That is to say, we went through the content, we didn't get through all of the examples. One of the things we talked about on Friday was a review of what we did the day before, which was conservation of mechanical energy. So when we did those problems where we had pendulums or roller coaster cars on Thursday, we were dealing with mechanical energy being conserved, and the idea here is that no heat was produced. And remember, if no heat is created, then that means there is no frictional forces. So you're associating heat with energy, but the force that produces heat is called the force of friction. As well, no work is being done. And I'm being a little facetious, but what I mean by that is, you know, if it's a box sliding down an incline and there's no friction, no heat is being produced, if I'm saying no work is being done, that means there's not like a monkey running along pushing the box or pushing the box backwards or forwards. It doesn't matter which direction. No additional work is being done to the system. And that means that the kinetic energy and the potential energy to begin with have to be equal to the kinetic energy and the potential energy later. You know, the kinetic energy later might be less than it was to begin with, but the potential energy later is going to be more. We then moved into, well, what if work is done? Well, if work is done, then the work done is the change in energy, and this is called the work energy theorem. And this was what the problem set that you were assigned is focused on. Basically, the work can be calculated by taking the force times the distance, and then final energy minus initial energy is exactly what we're talking about here. The final energy and the initial energy. It's the same thing we were talking about with conservation of mechanical energy, but there's some work being added. And we also talked about what if there is heat? Well, then the mechanical energy before equals the mechanical energy afterwards plus the heat, and the heat can be found using the force of friction times the displacement. So that's where we were, but I told you that since all of the examples we did were applications where work was being done, that you were to work on assignment 2. Is that correct? Okay. Fire away. Yep. Number 5. Okay, so let's look at number 5. A student throws a 1 kilogram rock vertically into the air with an average applied force of 18 newtons. The displacement over which the rock moved while the force was applied is 0.3 meters. What was the speed of the rock as it leaves the student's hand? Let's just leave that second question for a little bit. When I say to you, well, I guess maybe we'll answer it first. When I say to you that a student uses an average force of 18 newtons, that's an applied force. Okay? So the applied force has a magnitude of 18 newtons. In your formula for work equals force times displacement, that force is the applied force. Whenever you use F equals ma, that force is the net force. Okay. So let me write down what the displacement is. The displacement is 0.3 meters. We have the ability, since you know the applied force and the displacement, you can figure out the work done. Now, here's where the rock starts, and here's where the rock ends. So this is the rock. I'm not going to bother trying to draw the person's hand. They're holding the rock. They apply a force with their hand around the rock over that distance, and then they let it go at that point. So what kind of energy does the rock have here? Well, the answer is it has no mechanical energy. We don't know how high above the ground the person's hand was before they threw it. So we have to use this point as a reference point. And that's, you know what, that's a smart move anyway. Why wouldn't we just use that as h equals 0? And the person is standing there with the rock getting ready to apply the force. Up here, the mechanical energy will be equal to a sum of kinetic energy because it's moving plus gravitational potential energy. And if no work was done, and I don't know how the rock could get from here to there with no work being done, but if no work was done, then this energy at the top would be equal to the energy at the bottom. But work was done. So the idea is that the work done is the change in energy, which means the work done by the student is the final energy minus the initial energy. It's always final minus initial, always. There is one exception to that in physics 30, but that's a long ways off. This is force times displacement. Final energy is 1/2 mv squared plus mgh minus the initial energy is 0. So this is the setup for this question. This will be 18 newtons times 0.3 meters. I'm not going to bother to put in the units. This is 1/2 times the mass, which was 1 kilogram. It's a pretty big rock, but times the speed squared plus the mass times 9.81 times 0.3. So I have to take this number, 18 times 0.3, and subtract the 9.81 times 0.3. Then I have to, I guess you could divide by 1/2, but I like to just say multiply by 2 and then take the square root. Let's see where that takes us. So there's my left-hand side. I have to subtract 9.81 times 0.3. This gives me this number. That's equal to 1/2 v squared. So I have to multiply that by 2 and then take the square root of the answer and get 2.2 meters per second. Are you okay with that? Okay. Although, everybody, compared to what I'm going to show you, although this is relatively quicker, a little more thought has to go into this. Okay. There's an alternate way you could do this, which maybe requires less thought, but to me is more involved. And that's to say that VI of the rock is 0. The displacement of the rock is 0.3 meters. We want to find VF, but we're missing the acceleration. So how do we find the acceleration? Well, F net equals ma. So I can put in the 1 kilogram and the A. The question is, what do I put in for the force? It's not 18 newtons. Do you know? 18 minus the force of gravity. Right, 18 minus the force of gravity. Because while that rock is being worked on by the applied force of 18 newtons up, there is a gravitational force rather of 1 kilogram times 9.81. So that's going to give you 9.81 newtons down. And when you look at this diagram, the net force will be that 18 minus the 9.81. Let's try it this way. And, you know, I happen to think this method is more complicated and it's more thought, I think. I think if people tried this method, they'd be likely to put 18 newtons in here instead of 18 minus 9.81. So 18 minus 9.81, this is the net force divided by 1 kilogram means that's the acceleration. And I can use Vf squared equals Vi squared plus 2AD. And I don't know, you might disagree with me on which one is better or quicker or easier, but I'm just showing you both methods. So I'm going to take, well, Vi is 0, so 2 times A times D. You get the exact same answer. So, you know, operationally speaking, it doesn't matter which method you use. But I think energy is easier to work with. Then I don't have to think about vectors. Other questions? Yeah? Number 6? Okay. So a box slides along a frictionless surface, while traveling at 2.1 meters per second. Let's just break that down. Here's the surface. This is going to be the box when my computer catches up. And it's moving along at 2.1 meters per second. That means, since it's frictionless, that it continues with that speed as it's moving along the incline. But what's going to happen is it's now going to bump into a spring. So the spring is anchored to this wall, and it's attached to some plate which the box is going to connect with and compress the spring. So does the box, when it encounters the spring, undergo a change in energy? Yes. And there's many ways to think of this, but I'm just saying, since the kinetic energy is going to decrease to a stop, the spring is going to compress and the box will stop. That means it undergoes a change in energy. And again, Jay and everybody, there are a couple of ways to think about this, but I'm saying this is the change in energy of the box, and this is the work done by the spring. So when you talk about a change in energy, it's a change in energy of some object. When you talk about the work done, it's the work done by something. Well, that would mean that if this is EKF minus EKI, and it stops, the box stops, that means that we're going to have 0 minus the initial kinetic energy. In other words, looking at it this way, everybody, the box undergoes a negative amount of work. I should say that differently. Something does a negative amount of work to the box. And the reason for that is that the force that the spring exerts on the box is to the left in my diagram, and yet the object was moving to the right. Now, how do we calculate the force that the spring exerts? The force that the spring exerts is equal to kx. Now, this is one of the few cases. Let's just leave it. I was going to say this is one of the few cases where we should put that negative in front of the k, but I'm not going to. Let's see. You know what? This is a case where that's not helpful, because we want to know the force, right? So, and by the way, I've written something incorrect here. I didn't complete my thought. What else do I need to add? The displacement. In my head, I remember thinking, okay, so work is force times displacement, and then I thought, I better explain what that force is, and I got way ahead of myself. It's force times displacement. So if you want to know the force, then you have to take, let me rewrite this. I just have the force times the displacement equals negative 1/2 mv squared. I think we have all the information we need, don't we? Let's see what happens. The force equals, I'll divide later. Is it 2.3 times 10 to the negative 2 meters? Yeah? I'm going to leave the units out. Equals negative 1/2 times the mass of the box is, well, we got a bit of work to do here, don't we? What do we need to do here, Nate, to find the mass?
Get it from 4 newtons to kilograms.
And how do I do that? Alex? Oh, Alex. You just appeared like a genie.
No, you divide it by 9.81.
Good. You divide by 9.81. So what we're looking for here, Nate, is this formula on your formula sheet. Force due to gravity is the mass times the gravitational field. So this is 4 newtons. Mass times 9.81 newtons per kilogram. I mean, you're going to get very close to 0.4 kilograms, but I'll actually calculate it. 4 divided by 9.81 gives me 0.4077. I thought I saw, times v squared, which is 2.1. So not much for rearranging here. I'm going to take negative 0.5 times, I still have that number there, yep. Negative 0.5 times my mass times the 2.1 squared, and then I need to divide by that 2.3 multiplied by 10 to the negative 2. And this is what I get. And this is the weird thing about that work formula. Work is not a vector, but you can still use it wisely, that work equals force times displacement formula. You can still use it wisely, and if you get a negative F, that just means the force is in the opposite direction. So the answer is 39 newtons. And that's the average net force exerted on the box by the spring. It happens to be negative 39 the way I've thought of it, because that just means the force is opposite to the direction of the motion. There's something implied in this sentence, though, when it says, what is the average net force? It's just, what's the magnitude of the average net force? But does that make sense, Jay?
What if we had to find the spring constant?
Okay, so I'm going to do that. I'm going to find the spring constant here. But then I'm going to do it in a couple of different ways. Okay. If you wanted to find the spring constant, then one of the ways you could do it, and that's actually what I thought we were going to be doing, would be to take F equals kx and use the force we find to find k. But the force we find is not F in that F equals kx formula. This force of 39 newtons is an average applied force by the spring. And this is going to require either a lot of words to explain or a graph. I'm going to do words first. And let's just say that the spring goes from being in this state to in this state. 5 coils, 5 coils. the force required to put it to here is quite small. The force required to compress this to here is bigger. The force required to compress it to here is huge, right? And it's this force that's the force relating the spring constant to the displacement, because the spring constant is so many newtons per meter at a point in space or time. If you're told the average force is 39 newtons, then this force is 78 newtons. It's twice as big. The way to explain it graphically, and by the way, your question opens up all kinds of things we should talk about. The way to explain it graphically is to look at Hooke's law. And remember that if you want to take a force and a displacement to find k, they have to be a force and displacement at a point in time. We could take this force and this displacement, or this force and this displacement. So the force that we actually found was the average force, which would be halfway between 0 and the maximum. And that explains why this force is going to be 2 times 39. I apologize for not explaining where the 78 came from. I just wrote 78. So if you wanted to find the spring constant, then what we could do is take that and double it, which would give you 78 newtons, equals k times that 2.3 times 10 to the negative 2 meters. Now, I'm not done, because I want to show you something else once we get this. So here's my force. I need to double it. I'm going to drop the negative. Technically speaking, there is a negative in this formula, so that's why we can drop it. But my modification to this formula has always been, as far as I've told you, just drop the negative and just talk about magnitudes. So I'm going to take that, get rid of the negative, and divide by that 2.3 times 10 to the negative 2. That's the spring constant in newtons per meter. Good? Now, I told you at the beginning, and I said it 3 or 4 times, one of the ways to look at this is this way, is to say that the work is done by the spring. There's a totally different way to look at it. And it's maybe what you would want to do. I don't know. It's to say that no work is done No work is done. There's no friction, which means mechanical energy is conserved. Which means EI equals EF. Well, this is kinetic energy of the box, isn't it? When the kinetic energy of the box is reduced to 0, if I'm saying no work is done and I'm saying mechanical energy is conserved, I'm saying that kinetic energy is now stored somewhere else. Where is it? In the spring. And we call that spring potential energy, which is 1/2 kx squared. No force, no work. If I want to find k, I can multiply both sides by 2 and get mv squared equals kx squared. So k will be equal to mv squared over x squared. And I don't have to think about that average force, maximum force, applied force. What I can do is just take the mass of this number, multiply by the speed squared, divide by the displacement squared, and it's like a miracle. I get the exact same answer. And anytime you're dealing with trying to find a spring constant, if there's energy involved, this is the way to go. To think of it not as the spring doing work, but to think of the spring getting energy. Other questions? Yeah.
Number 4.
Okay, let's look at number 4. What is the average net force exerted on a bullet, a 4.5 gram bullet, if the expanding gas in the barrel of the rifle or gun moves the bullet from rest to a speed of 1,000 meters per second over a particular displacement? So work is done. Work equals change in energy. This is work done by the gun. This is change in energy of the bullet. And by the way, this question, and in fact maybe most of these questions, could be solved using kinematics and dynamics. Because you can use F net equals ma and you can use kinematics. But this is a more direct approach. The work done by the gun is the average applied force times the displacement. The change in energy of the bullet, don't forget this is final minus initial. So it's going to be 1/2 mv F squared minus 1/2 mv I squared. And Nate, what can you tell me about 1/2 mv I squared? It's 0. So we don't need to worry about it. The average applied net force, and I'm using applied and net and average here all together because there are no other forces, times the displacement. How long is the barrel of the gun? How long is the 0.7? So it's a long gun. 0.7 meters is like this. It's not a handgun with a big long barrel. It's probably a rifle. 0.7 meters equals 1/2 times the mass. I think I saw 4.5 times 10 to the negative 3 kilograms times the speed. It was 1,000. Don't forget to square the speed. And again, could you do this with dynamics and kinematics kind of mashed together? F net equals ma and VI, VF, AD, all that stuff. Yes, but this is nice and clean and quick. 0.5 times the mass times the speed squared. So this is the kinetic energy in joules that the bullet will have, which is the work done by the rifle in accelerating the bullet. So if I divide that by the displacement, I will get the applied force. So about 3,214 newtons. 3.2 kilonewtons is what we have. Is that good? Okay, we're going to move on. We're going to look at a couple more examples today, and then you're going to finish off this assignment. And I'm still going with your exam being on Monday, a week from today. Correct me if I'm wrong, just look back a page or two. We did examples 1, 2, and 3, but we stopped there. Yeah? Okay. So we're looking at example 4. We have an inclined plane. I don't know if you remember, but if you were to think back or even flip back to the previous unit, solving problems involving accelerated motion on an inclined plane when there was friction got messy because we had to find parallel and perpendicular components of gravity, and we had to equate the perpendicular component of gravity to the normal force, and we dealt with coefficients of friction. Energy is cleaner than forces in kinematics. The work is less complicated. A 20 kilogram box slides down the ramp that's shown from the top. The force due to friction is 55 newtons. How fast will it be moving at the bottom of the ramp? How fast will the block be moving at the bottom? So, is mechanical energy conserved? Why not?
The friction, which means heat loss.
Right. There's a force of friction, which means some of the mechanical energy is converted into heat energy. Heat is lost. And when we say lost, it's kind of a weird way to say it. It's not wrong. But what it means is it's produced. It's created. It's lost from the mechanical energy, and now the surface of the incline is warmer, the box is warmer, a little bit of the air is warmer. So mechanical energy is not conserved. Is any work done to the box?
Just the potential gravity, potential energy.
Right. But now, and this had to come up sooner or later. This had to come up sooner or later. How many of you would say that, well, doesn't gravity do work? But since we have a special way to calculate that work called potential energy, we don't consider it doing work. It's kind of like in the example we just did with the spring, when I said, if we say the spring doesn't do work, then I just use the formula for spring potential energy. So there's no work done. In other words, there's no monkey pushing on the box. There's no work done, but there is heat produced, which means that we basically say the energy before equals the energy after. Now, I want to make a real important point here. I haven't lost my head. Well, that's maybe a different question. I'm not saying mechanical energy is conserved. I'm saying energy is conserved. If I were to write this, I would be wrong. That is not what I'm saying. I'm saying that the energy at the top of the ramp has to equal the energy, well, I'll say at the bottom of the ramp and then amend that. I'm saying the energy that exists when the box is at the top is equal to all of the energy that exists by the time the box gets to the bottom. I'm saying it that way because the heat is not all at the bottom. That's right, it's spread out throughout the whole trip. So this is mgh. It's gravitational potential energy. The box presumably will be moving when it gets to the bottom, plus heat. Heat is a type of energy. How do we calculate heat? There's a formula for heat. Unfortunately for all of you, it's not on your formula sheet. But if you remember that heat is work done by friction, and you know that work equals force times displacement, then the work done by a monkey is the force the monkey applies times the displacement. The work done by a winch is the force that the winch applies times the displacement. The force done by friction, or the heat, which is produced by friction, would have to be the work done by friction, which is the force of friction times the distance. Can I cancel those masses? No, I can't. When you cancel masses, what you're really doing, don't write this down, is you're dividing both sides of an equation by m. I can't divide the force of friction times the displacement by m. Well, I can, but then I'd have to write over m. I can't get rid of the masses here. If we were after a coefficient of friction, and you decided to change this force of friction to mu times the normal force, and the normal force is mg, then you could cancel. But we're not after that. So I'm going to put in the mass, 20 kilograms, times 9.81 newtons per kilogram, times the height. H means height. You need to determine this number. Do so for me, please. I believe it's going to be 6. It's just the Pythagorean theorem, right? 10 squared equals 8 squared plus the height squared. So I get 6 meters here equals 1/2 times the 20 times the V that we don't know plus the force of friction. I think we were told how many newtons it was, 55 newtons, times the displacement. What are we going to use for the displacement? Alex?
It would be the 10 meters.
It would be the 10 meters. The 55 newtons, I said I was leaving out the units, so the 55 newtons is being applied to the box for all 10 of those meters. It's the actual physical distance that the force is being applied over. Numerically speaking, look everybody, this is just a number. This is a number times V squared. This is a number. To solve this for V, you would just take A minus B divided, or A minus C divided by B and take the square root. The math here is pretty simple. I'm going to give you a minute to do the calculations. I don't think you'd want to do it on your calculator in one fell swoop. I think you'd probably hit equals at some point. This is how I would proceed. 20 times 9.81 times 6 minus 55 times 10. Now I'm going to multiply by 2 to get rid of that half. I'm going to divide by 20 to get rid of the 20. And then I can take the square root and get 7.9 meters per second. And believe me, if you tried to do this using forces on inclined planes, how we did it before, what you would have to do is find the net force down the ramp to find the acceleration and then use kinematics. I think it's a lot more work. So I get V equals 7.9 meters per second. Anybody else get 7.9 meters per second? Good. One last example. And this is the penultimate example. Because first of all, mechanical energy is not conserved. So I'm just going to write that down. You can write it down if you want, but mechanical energy is not conserved. Why not? Nate? That's not good enough to say because it's accelerating, because a pendulum accelerates, but mechanical energy is conserved. Jay? Friction acts. There's a force of friction, and I'm glad you said force, not just there's friction. There's a force of friction, which means heat is produced. Heat is produced, mechanical energy can't be conserved. What if I could blink my eyes and snap my fingers and change it so there was no force of friction? Why would mechanical energy still not be conserved in this example? Yeah. There's an applied force, so work is done. So up until now, we've either dealt with mechanical energy being conserved, or heat being produced, or work being done. Here, work is being done and heat is being produced. So that heat being produced is energy that's being bled out of the system, but we're doing work, so we're adding energy to the system at the same time. We approach a problem like this by saying work equals change in energy And I'm going to back up and look at the previous example. Nope, I'm going to look at stuff from the previous day. So I'm actually going to go to an example we did like this one. Remember doing this one? The rock? Would I be allowed to write the subscript mechanical here beside the E in the rock question? Is the work done the change in the mechanical energy of the rock? Yep. Here, would I be able to say the work done is the change in the mechanical energy of the bullet? Sure. 1/2 mv squared is mechanical. In question 6, would I be able to say the work done by the spring is equal to the mechanical energy change of the box? Yes. When I look at this question, whoops, is that it? No. When I look at this question, am I allowed to say that this is the change in mechanical energy? No, because there's another type of energy. So this is not just mechanical. What's the other type of energy? Heat. Excellent. And I'm really glad that we're all saying heat or force of friction or heat energy. We're not saying energy is lost to friction. Bad thing. Energy is lost to heat caused by a force of friction. So what happens? I get work equals final energy minus initial energy. Work done is the force applied times the displacement. That's easy. What does the box do in this example? The box is sliding along, accelerating from 2 meters per second to 8.5 meters per second. It's on a level surface, so there's no change in gravitational potential energy. That would be more complicated, doing this up a ramp. But there's no potential energy. The box does have an initial speed, so it has an initial kinetic energy, and it has a final speed, so it has a final kinetic energy. So we're going to have EKF minus EKI. But, and just stop writing for a second, I'll save you some eraser time. Why is that wrong?
Wait, never mind.
Change your mind? I got all day. Change your mind again? Go ahead.
Because it accelerates?
No. In fact, because it accelerates, that's why final kinetic needs to be, initial kinetic needs to be subtracted from final kinetic.
Would we have to add the applied force to EKF?
Would we have to add what?
The applied force to EKF?
The applied force is over here, and by the way, we would never apply a force or add a force to an energy. Yeah. I have to add the heat. Heat is a type of energy. This would be true if there was no heat. But now my question is, where do I add the heat? Is heat initial or final energy? No, not both. It's tricky, though. A 50-50 shot. What do you think? Is the heat something we're going to include as an initial energy or a final energy? final. Because initially the box is just moving along at that speed. Friction hasn't acted on it until, I understand why you say before and after. Because friction is acting from the beginning, right? But if you take a snapshot of that point in time where it's moving at the 2 meters per second, is that right? At that point in time, it hasn't slowed down yet, so none of the frictional force has been doing anything. That heat is bled out of the system over the whole interval, but it's accounted for at the end. At the end, if you could magically see how many joules of heat were there, that's when you would look to see how much heat is produced. So what we need to do is say EK final plus the heat minus EK initial. So, beast of a question, we end up with FD equals 1/2 mv squared afterwards plus the force of friction times the displacement, because that's how we find heat, minus 1/2 mvi squared. I think maybe the first time we've had any kind of application, whether it's forces or energy, that had 4 pieces to it. Alex, you're going to help me out here. What is the, are we trying to find the applied force?
No, we're trying to determine the force of friction.
Okay. What is the applied force?
120 newtons.
120 newtons. And over what distance is it applied?
13.
13 meters. What is the mass of the object?
9 kilograms.
And the final speed is 8.5?
Yes.
The initial speed is 2. Okay. I want us to calculate all of these pieces separately. So let's calculate what 120 times 13 is. And I think it's going to be 1560. Okay. There were 1,560 joules of energy pumped into the system from beginning to end. Let's calculate what 1/2 times 9 times 8.5 squared is. $325.125 joules. This is the force of friction times 13. And when I calculate this, I believe it's 18 joules. I just want to, you can get the answer and we'll worry about getting the answer in a minute, but I want you maybe just not to write this next part down. I'm going to move the 18 to the other side. I mean, you have to do that anyway, but just don't worry about rearranging it. Don't worry about the answer. If I move the 18 to the other side, I get 1560 joules plus 18 joules equals the 325.125 plus this. Would you agree this is the heat? And this is the final kinetic energy? So this is all of the energy at the end. This is the initial energy. And this is the work. That should make sense to you. If there was initially 18 joules of energy in the system and I pumped in 1,560, then that means the sum of this is the total energy in the system afterwards. And some of it will be kinetic energy of the object, and the rest will be heat. Anyway, to solve this equation from here, we need to take the 1560, we need to subtract the 325.125, we need to add the 18, So I'm looking here at this line just above the calculator. I need to add the 18. This is the total amount of heat produced. I need to divide by 13 meters, so I get a force of friction of about 96 newtons. Any questions with that example? I guess I'll write down the answer. What did I just say, 96 newtons?
Yeah.
Thank you. You know, you could have done it with forces, but you'd have to say F net equals the applied force minus the force of friction. You'd have to find the acceleration from kinematics and work backwards to find that force of friction. And some of you might prefer that. I don't know. By the time you get to Physics 30, there are going to be some problems which either can only be done using conservation of energy, or the other way to do it is so complicated you would never want to do it the other way. So now you can work on assignment 1, which deals with situations where forces of friction are present. I would recommend making sure that you go through and do any of the remaining questions as well that didn't get done. Is it just part 1 and 2? I think so, eh? Okay. And then in tomorrow's class, we'll look at power, and we're going to be either reviewing 3 days this week or maybe doing another lab. We'll see. There's a lot of material in this unit to go back on. We've kind of moved away from circular motion recently, but that's part of the unit too. So get to work on that stuff, please. I just need to do a couple of quick things, and then I'll come around and I'll give you a hand.